Our next speaker is Ryan Burke. So I'll let Ryan take it away.
Thank you. Hello, everyone. My name is Ryan Burke. I'm a senior coastal engineer at Anger QEA, and I'm from our Austin, Texas office. I'm here to present about the Boggy Cut GIWW stabilization project. So there's a handful of stakeholders I'd like to thank: Matagorda Bay Foundation, Texas General Land Office, Port Bay City, the Army Corps Galveston District, and TxDOT for their roles in the project as well. So ultimately, we'll be going through the project location, some of the historical aspects, the project goals, the design itself, and the habitat restoration components, project implementation and some of the challenges, and ultimately discuss some of the beneficial use in Texas. So the project location is in East Matagorda Bay. You can see our project review area right there. It is an underutilized placement area 104 by the Army Corps. So ultimately has not had any placement as of late. So resulted in about 3.5 miles of open water that causes navigation impacts and shoaling within the GIWW. So the history, just in general, the GIWW itself spans from Brownsville, Texas to Okeechobee Waterway in Fort Myers. The Texas portion itself is 426 miles long and runs from Sabine Pass to the Brownsville Ship Channel. Ultimately, the inception of the GIWW came from the General Survey Act of 1824, which is where Army engineers were authorized to go out and start surveying locations for canals. That paved the way for the idea of the GIWW itself, and then ultimately the long construction of the GIWW. The last section was completed in 1949, which spanned from Corpus Christi down to Brownsville, linking Mexico to Florida. As part of the project, during the dredging, they had sidecast the material, ultimately creating barrier islands. Those barrier islands provide protection from storms, erosion, and also help keep sedimentation out of the channel itself. So here you can see just a historical context. The top left photo we got in 1965, so about 20 years after the stretch was cut. And then ultimately in 1995, you can see that there's a pretty large chunk that's been reduced. And then ultimately in 2024, we have pretty much nothing left there. Marsh habitat loss in Texas. As it stands today, we're losing a rate of 5,700 acres annually. This is a cause of erosion, subsidence, relative sea level rise, and many other factors, but ultimately insufficient sediment supply is the major cause and impediment to the restoration efforts. So here you can actually see a couple of photos of vegetation within Big Boggy Bayou itself, degrading due to some of those coastal processes. So the project background, Matagorda Bay Foundation, with funding from GLO's KEPRA and match from Port Bay City, ultimately came together to advance a restoration effort. So this restoration effort includes a breakwater, island habitat restoration, marsh restoration, and ultimately some oyster reef habitat as well, in the hopes to solve the GIW shoaling issue, navigation traffic impacts, and then help aid the recession of Big Boggy National Wildlife. So our project goals here are mainly resiliency to reestablish the barrier island that was previously there, so reduce sedimentation in the GIWW itself, reduce the wave fetch within the navigation channel, and help protect Big Boggy National Wildlife, and ultimately have those various habitat restoration components I previously mentioned. So the design and the habitat restoration. This project was originally part of the M8 Coastal Texas Protection and Restoration Feasibility Study project. So ultimately you can see here in the yellow, we've got the sediment source for the project itself, and I know it's a little bit zoomed out, but on the northern side of the GIWW, it was also supposed to include some marsh restoration and breakwater as well. But for our project here, we're just gonna be focusing on that main island component that you see in the project area there. So here's the full layout. You've got your breakwater. Oop, because I don't know how to use the laser. There we go. You've got your breakwater component up on the GIWW spanning the full project site, and then you've got your island, your marsh, and your oyster reef, and then just a typical cross section here. You've got your breakwater, a little bit of a gap between the island, a slope of 5 to 1 on that island component. You've got your marsh restoration habitat, and then you've got a confinement berm on that side to help protect some of that marsh habitat restoration. And then at the very end, this purple block is the oyster reef habitat. So the breakwater is approximately 3.5 miles long. It'll help provide protection from the wind-generated waves in East Matagorda Bay, ultimately protecting Big Boggy National Wildlife and the GIWW itself. And it'll reduce that sedimentation, and it'll also help protect some of the habitat components from ship wakes as they are navigating through the channels. Our Rookery Island habitat restoration will be approximately reestablishing 100 acres of island habitat with varying widths of 170 to 260 feet. And the restoration benefits associated with that are nesting habitat, and then also provides beneficial use of dredge material placement. For our marsh habitat restoration, it'll reestablish about 200 acres of marsh habitat. So you can see the confinement berm here, and then the marsh on this side. And the marsh habitat spans between 150 and 650 feet, depending on which area of the project you're in. And then ultimately those benefits are marsh vegetation via natural recruitment, habitat for fish, shrimp, and crabs, as well as other organisms, and then ultimately we also aid in the beneficial use of dredge material placement. Our oyster reef habitat is approximately 4 miles of reef. It'll be constructed of materials either mulch, crushed concrete, or stone, and be utilized for those oysters to grow on. It'll increase the oyster population and provide habitat for other organisms as well, and reduce some of that incoming wave energy for the marsh and island restoration components. And on here, you can see this is actually a fairly newly constructed project, obviously ACBM, so not quite the same materials, but the oysters were starting to grow within 4 months post-construction. So our project implementation and challenges. We've got data collection at the forefront, design, review and package preparation, and then ultimately construction. Currently, we're in our design stage, so all of the previous ones that you've seen were from the feasibility study in the coastal Texas by the Army Corps and GLO. Our constructability and tidal flushing aspects. So the project challenges are that the entire area is within pretty shallow depths. As someone mentioned earlier, most Texas bays are 2.5 to 3 feet, so that's the depths that we are facing with this project. It is adjacent to a navigation channel, so you got to be mindful during construction of not impeding that aspect. Ultimately, we've got some pretty large habitat components. The breakwater is going to go to about 7 feet and AVD 88, so it'll be a pretty tall structure and pretty heavy as well. And then the island restoration component is going to be 9 feet and AVD 88, so we'll be having to handle quite a bit of settlement on that component. And then also there's a lot of existing habitat within the area, both wetland and oysters. One other component that we need to account for is tidal flushing. So within that marsh habitat, we'll be adding some tidal flushing aspects to help with beneficial exchange of nutrients, promoting healthier plant growth and supporting wildlife, and then also help establish the hydrology of the restored marsh, preventing stagnation as well. So beneficial use in Texas. Fairly new initiative, but it is a challenging component and ultimately plays a factor in this project as well, since that's the main goal. It's got the potential to restore thousands of acres of degrading coastal habitat annually, as the benefit of increasing coastal resiliency and abating local sea level rise. So some of the efforts that are ongoing or getting kicked off here are the Army Corps of Engineers 70-30 policy or philosophy, and then the Texas GLO Coastal Resiliency Master Plan, the Texas GLO Sediment Management Plan, and then Ducks Unlimited Texas Beneficial Use Master Plan. So there's a lot of interest, but very few projects, and then the challenges associated with that beneficial use are timing, permitting, and funding. And in order for them to work quite a bit of coordination is required. That's the reason we have quite a few handful of stakeholders involved in the project. So the Texas Beneficial Use Master Plan, I won't go into too heavy of a detail because my colleague Rebecca will be giving a talk on that tomorrow. But ultimately, the project goals are to coordinate efforts, identify efficiencies and build consensus, identify and prioritize projects, and then provide some 10% plans as well as guidelines and adaptive management approach that result in some cost savings. So the whole effort is to streamline the future BU projects across Texas and to prepare sites for some potential funding from various aspects. Any questions? What was that question again? Sorry, I didn't quite hear you. Yes, so that's actually still an ongoing effort that we are currently looking into through a few different avenues. Parker's Cut, dredging. So yes, that is still in the works, but not associated with this particular project at this time. Any other questions? Nope. All righty, thank you all.
Thanks, Ryan. All right, our next speaker is Charlotte Nash.
Thank you. Hi, everyone. I'm with the Nature Conservancy, and I'm going to be talking about our Texas Wetland Action Mapping Project. So for the scope of this project, we're talking about tidal wetlands in Texas, which is salt marshes, mangroves, brackish marshes, and tidal flats. And these are really important ecosystems for nursery, for commercial and recreational fish and shellfish species, habitat for threatened and endangered species, flood mitigation and storm surge reduction for communities, as well as having extremely high rates of carbon storage. However, we are rapidly losing tidal wetlands in Texas due to many factors like relative sea level rise, development pressure, hydrologic modifications, changes in federal policy and protection, as well as barriers to tidal marsh migration. So marshes who may be able to move up and up the shoreline with sea level rise are in many cases being blocked from due to development or roads and water control structures. So why are we doing this Texas Wetland Action Mapping Project, or we call it Texas WAM? It is with the ultimate goal of reducing and reversing that tidal wetland loss in Texas. And that is a very big goal. So we have brought together many stakeholders with us in this process. It's a stakeholder-driven process. And we believe that that's the way to do it. By identifying consensus-based priority areas together, we can increase funding and collaboration opportunities for tidal wetland restoration and protection in Texas. So here's a look at our working group so far. It's a great diverse group of planners, practitioners, agency staff, NGOs, land trusts, landowners. And if you're interested in joining, you can come up to me after the talk, or I'll have my email at the end. There's still time to join the working group. So our objectives are to ultimately produce a Texas Wetland Action Plan that will show where and how tidal wetlands should be protected and restored. We're doing that by identifying consensus-based high priority areas, looking at where the high priority areas overlap with co-benefits like biodiversity, carbon storage, flood mitigation, and developing a map of those high priority, high co-benefit areas with the recommended strategies. So here's a look at our process, and I'll go through each of these in a little more detail. But we started with existing data and we created opportunity maps that show where different wetland conservation restoration strategies are likely suitable and where they're likely needed. So we have they highlight different areas of the coast based on where they're suitable. So the opportunity map for protecting wetlands is going to look different than an opportunity map for improving management of migration space, wetland migration space, for example. We also produced co-benefit layers showing where wetlands are providing benefits to people and nature. And we went through a participatory mapping exercise with our working group. We brought together all of those three, the data layers, the opportunity maps, the co-benefit layers, and we asked them to work together to select those priority areas. So we ultimately produced 6 opportunity maps for Texas, 4 that are focused on near-term protection, near-term help for tidal wetlands, so protecting wetlands, employing beneficial use of dredge material, restoring hydrologic flow, and implementing living shorelines, as well as 2 that focused on sustaining tidal wetlands for the future, so protecting migration space and improving management of already protected migration space. So for example, at TNC, we have some coastal reserves that are future migration space, but we're not currently managing them in a way to facilitate wetland migration. So we're starting to do that work now. We produced the co-benefit layers based on feedback from the working group. We asked them how they wanted to prioritize action areas, and they said based on where multiple co-benefits align. We asked them what they thought were the most important wetland co-benefits, and we created layers based on that. So we have layers of priority habitat, flood mitigation, social vulnerability to hazards, improved access to parks, and carbon storage. And in the participatory mapping process, we also said, we encouraged the working group to use their local and expert knowledge in addition to the layers. So what we were hoping to get out of the participatory mapping, and we did, are these action areas. And they can be made up of 1 or more planning units. That was just our base unit. They're 5,000 hectares in size, and it's a hexagonal grid across the Texas coast. And 5,000 hectares is the median size of a wetland complex in Texas. Our ultimate goal is to refine it down to 3 to 5 action areas per GLO planning unit, planning region, or 12 to 20 for the entire coast. And we are requiring that each action area has a lead organization and associated partners who are going to continue planning and hopefully implement projects in those action areas. So for the participatory mapping process, we created the Texas Wetland Action Mapping tool where we put all of this data. I just wanted to show some screenshots from that tool, but it had all of our data. This is the sum on the left. We have a heat map showing the summary of all the co-benefits together laid out across the Texas coast and at the planning unit scale, so it's not as refined. These are all our our opportunity maps. And then we also asked the working group to share with us their previous priority locations where they're already working and where they're already interested in working before this process, as well as many, many supporting data that we had in there. And this tool was really just used as for decision support. So we were having in-person conversations with stakeholders, and it was really just meant to generate those conversations. And we were okay with it if our working group created action areas not at all based on what the data in the tool said, just based on their actual knowledge and experience and priorities for their organization. So these are some pictures from the participatory mapping. We had 3 workshops in person. So we had one in Houston, one in Corpus, and one in Brownsville at UTRGV. And so we first had everyone come together. We split them into small groups, and we asked them to explore data in the tool through a couple different lenses. One was thinking about wetlands for their co-benefits, then actions for the near term to sustain them in the near term, and then thinking about the future and where wetlands will be in the future. And then we all came together in each region and we talked about where we wanted to work, who could work with who could be a lead organization, who would be more comfortable being a partner. And we used these hexagons as these hexagon fills just as kind of a visual tool for the discussion. So you can see, I don't know how to use the laser, but in the top where it's darker, that we basically have everyone place down their action areas. And so the darker fill is where more people have indicated that that's a planning unit of interest for them, or they would form an action area comprising of that planning unit. So this created a lot of data that we're currently working through. We just did that exercise back in February, and we're currently looking at what everyone has submitted and evaluating the different draft action areas for opportunity map acreage, for alignment with co-benefits, for who the partners are, and we did it in 3 different iterations. So we're going to bring everything together and bring back to the working group what they proposed, and ultimately decide at our next workshop on the final wetland action areas. And we're getting close to the end of the process, and by late summer of this year, we'll have that Texas WAM plan. So thank you very much.
We have a few minutes for questions, if anyone has a question. Yes. So for Zoom, the question, if I am repeating it right, is what about the state's ability to change these plans at their whim? Has the state bought into this idea?
I don't know if I'm the best person to answer that question, but I will say that we are just hoping that having lots of stakeholders come together and identify these areas as priorities will build momentum and will show that, yeah, there are many people behind this plan. We hope that it will be a resource that people can use and cite in funding proposals. But yeah, hopefully it will be useful.
Thank you, Charlotte. Our next speaker is Mission Arandis' own new Margaret A. Davidson Fellow, Kelly Savage.
Wow, that was great. Wow, Kyle. Thank you for that introduction. Hi, everybody. My name's Kelly Savage. I'm a PhD candidate at Hart Research Institute, and today I'm going to talk to y'all a little bit about my research looking into the carbon storage potential of oyster reefs. So to get started, I want to talk about 2 main processes that are driving carbon cycling on oyster reefs. There's a lot of complex ways carbon can be cycled on a reef, but these are the 2 main drivers that I want to talk about today. So oyster reefs can be a potential carbon sink, and the way they're a sink is they are filter feeders. So they're filtering this photosynthesizing algae out of the water column and storing it within their reef sediments, along with other sediments that were suspended in the water column, and they're creating this carbon burial over time with the sediments and organic carbon, thus creating this potential carbon sink within the reef. Oysters can also be a potential carbon source through calcification. When oysters are forming their shells, they can shift the water chemistry of the water column, decreasing the amount of carbonate and increasing the amount of carbonic acid, which could potentially lead to an off-gassing of CO2. So this inorganic carbon trapped in these shells is originating from this carbon releasing process. Thus, they can be a potential carbon source as well. So because these two processes are happening, are reefs overall a net carbon sink or a net carbon source? If we can understand this question, then we can start to provide this missing link to the coastal carbon cycle. And it would have great ecological implications because oyster reefs are at risk. We have a 50% loss in the Gulf of Mexico. So we may be missing this really big key carbon sink because we have lost a lot of these reefs, and we wouldn't have this service anymore because they're lost. But we also may just be underestimating a source if we find that they're a source. And this is why we need to understand this information. And the way we do this is providing this foundational information to assess oyster reef carbon storage, and that's understanding one, carbon stock in a reef, and then also carbon burial rates. So you're looking at the amount of organic and inorganic carbon actually stored within the sediments of the reef. The organic carbon represents that CO2 removed, and the inorganic carbon represents that CO2 released. However, at this point in time, we only have 12 published studies globally looking at any kind of carbon burial rate. And in the United States alone, there's only 4 studies published. And of those 4, there's only been 2 that have been conducted in the field, actually going out into the oyster reef and measuring how much carbon is being stored on this reefs. And all of these carbon burial rates have reported this really wide range of reefs being sources and also reefs being sinks. So we need a lot more information, especially because there's no way to compare across studies because there's no standardized methods in terms of how they're doing these studies. But it provides this really unique opportunity in the Gulf because as you can see, there's a lot more information needed here. And the Gulf is very different than the East Coast. We have warm waters year-round in the Gulf, so oysters are actually growing year-round, and they're productive year-round, whereas on the East Coast, they go into this hibernation period, and they're only growing part of the year. So that's where my research comes in. We want to look at the carbon storage potential of reefs here in Texas, and the way we're going to do this is quantify organic and inorganic carbon per reef. And then we're going to look at to see if environmental setting affects the amount of carbon being buried within a reef, because there was a study that was done on the East Coast that found that environmental context matters. So whether a reef is near an adjacent vegetated or unvegetated habitat, or whether a reef is intertidal or subtidal. So for this talk, I'm going to show you all some initial findings, but it'll just be on the second question looking at habitat context. So the way that we conducted this research, we took reef core samples in St. Charles Bay. The reason we chose this bay is because it's been closed to commercial harvest since 2017. And there's reefs near varying adjacent habitats as well as reefs at different depths. So it's an ideal study area for us. We took reef cores at 20 stations across St. Charles Bay. And these reef cores we took through a vibrocoring technique where we basically vibrated an aluminum pipe through the entire reef structure to collect shells and sediments that have been accumulating over time over the life of that reef. And so we took these reef cores back to the lab, cut them open, and sectioned them every 5 centimeters to see how carbon's been accumulating over time. So this is that vibrocore cut open, sectioned every 5 centimeters, and then we took subsamples in each of those 5 centimeters to measure organic and inorganic carbon, as well as reef sediment characteristics, such as grain size, organic matter, and sediment chlorophyll A, to inform why we might be seeing differences in carbon budgets or carbon burial rates. Okay, so that's how we're conducting the study. Let's get into some initial findings. before I get started explaining this PCA, I want to give you the main takeaway that we're finding so far. So natural reefs are varying in their sediment and carbon composition by depth. So intertidal and subtidal reefs are varying in this. This principal component analysis is representing that average sediment and carbon composition per reef core. So each point on the PCA is representing a reef core we took out in St. Charles Bay. And the blue is representing our intertidal reefs. The yellow is representing our subtidal reefs. The triangles are representing reefs near vegetated adjacent habitat, and then the stars are representing oyster reefs near unvegetated habitats. Basically what this PCA is telling us is over 77% of the variation. Our PC1 is explaining over 77% of the variation that we're seeing in our data. We're seeing this gradient across the PC1 where we see sand on the left side, and it's associated with less organic rich sediments, to the right side where we see a lot of organic rich sediments with these finer grained silt and clay. And we see the subtidal reefs being associated with those organic rich sediments, and the intertidal reefs more associated with the sand sediments. And this might be due to the hydrodynamics of an intertidal reef versus a subtidal reef, and potentially like the depositional environment. We're not really seeing a difference between vegetated adjacent habitat and unvegetated adjacent habitat, which we weren't expecting, and we're gonna look into more. So this is a very similar PCA. I have the natural reefs up here still, and we added in restored reefs so we could see if restored reefs are providing the same service as natural reefs. This time, so before I get into it, natural reefs and restored reefs are varying by reef type. So we are seeing a difference between these restored reefs and these natural reefs. This time, colors representing depth again, but this time the not filled triangles are our restored reefs, and the filled triangles are the natural reefs. We're seeing a similar gradient as we did in the first PCA. PC1's explaining over 76% of that variation, with that gradient between sand and then silt and clay and more organic rich sediments. The interesting thing we're seeing in this PCA is some of our subtidal restored reefs are starting to cluster in the same area as our natural intertidal reefs. We might be seeing this because, one, they are a lot younger. These reefs are only about 5 years old, so maybe they're not quite providing that same service as the natural subtidal reefs and looking very similar, or because they're at a different place in the environment, because they're on this side of the bay, whereas the natural reefs are on this side of the bay. And this is something we're also looking into more. Okay, so the last initial finding I want to share with y'all today is some depth profiles. Each depth profile is a reef core that we took. So this depth profile is from this restored reef. This is just an example so you can see how carbon is accumulating over time and changing. Each point on the line graph represents those 5 centimeter sections where we took subsamples. So the first graph, we looked at shell percent, so how much shell was in that 5 centimeter section. And then we looked at organic matter percent and then grain size class. And then we separated this reef core into 2 sections for restored reef. So we have before reef. This is all just soft sediment before the reef was ever restored. And then we added this layer of shell material, and then the reef started growing, and that's the active reef portion. So as you can see, once the reef started growing, we see an increase in the amount of shell percent organic, and then all these fine sediments. So the main takeaway here is the restored reefs are trapping organic matter in these fine sediments. So they're starting to provide the service of potentially carbon storage. The next example I want to give y'all is a natural reef core. It's also a subtidal reef. And what you're seeing initially is this core is a lot longer, and it's because it's over thousands of years old. This reef is representing over thousands of years of organic matter and carbon accumulation. The main takeaway here is what we're seeing is organic matter is accumulating over thousands of years, and we're not really seeing a huge decrease in the organic matter. So potentially it's not being degraded or remineralized and put back into the atmosphere. Sorry, need to hold this closer. And you can see this because we separated this depth profile into active reef, historic reef, and the before reef. There's an increase in the amount of shell, organic matter, and fine clays and sediments as that reef started growing thousands of years ago. And then we see this storage of that organic matter over that lifetime of the reef. Okay, great. Okay, so the last thing I want to do is just wrap up this presentation. The key takeaways from it is that reef depth matters. We're starting to see it matters in carbon storage. We are also starting to see restored reefs are providing this service, and natural reefs resemble this long-term, they're starting to resemble this long-term carbon store. Right now, I'm finishing up calculating those carbon burial rates and determining if they're net carbon sources or sinks, which can inform a restoration suitability index map in terms of if they are a carbon sink, where could we place them on the Texas coast for this direct benefit of carbon storage. And with that, I will take any questions, potentially. Yeah. No? Yeah. Yeah, that's a good question. So the question was, how do you know if that where the before reef starts on that natural reef? Basically, I go into the reef core and I look at every single section, and when I see oyster reefs that are coupled, I know there was live reef there, and I knew that's when it started because that's where we started to see those shells. And before that, it was a lot of just sediment. Yeah, and shell hash.
Thanks, Kelly. Oh, I do want this.
Okay, our next speaker is Isabel Nykamp.
That's me. Hi, y'all. I changed up the title a little bit just to make the last talk of the day exciting. But today I'm going to be talking about quantifying human damages or tire tracks, ruts throughout the rest of the presentation on wind tidal flats using UAS or unmanned area systems and a based analysis. And actually, I am in this title slide up here. So if you can see, the tiny picture of me was taken with the drone. So let's get into it. But one of the first questions I asked myself when I started this project is, what is a wind tidal flat? So maybe not. Oh, yeah. Wind tidal flats are actually the dominant wetland type here in South Texas, and they are really hosted by some extreme impacts. So hypersalinity, high irradiance, and very irregular wind-driven tides, hence their name. And this really can change these wind tides in a matter of moments, going from this very dry and flat region to being inundated up to your shins in a couple of minutes to hours. So this is the exact same tidal flat area, just taken on a different day. And these extreme qualities really limit the amount of wetland plants that grow in this area and instead foster the growth of cyanobacteria mats, which can look, again, very different in times of very high radiance and dryness to this beautiful green photosynthetic cyanobacteria mat across the surface when it's wetted. And they are wonderful. They are the base of this system and really act as photosynthetic and important system which laminate the sediments in this region and host a lot of microbenthos and feed a lot of our migratory and overwintering birds. Unfortunately, as you kind of saw from this first picture, they look very unassuming to many people across this region, which can result in a lot of human damages or tire tracks across this region. Now, unfortunately, this tire track can have a lot of impact onto the hydrology and potentially the cyanobacteria crust within this region and can have potential to disrupt that base ecosystem in this region. fortunately for us, there's been a lot of growing interest in wind tidal flats for potential restoration as the importance of these migratory birds are really known and prevalent. So my project is looking at informing the extent and persistence of these damages across wind tidal flats in South Texas. So how we did this was pretty fun. I got to develop a replicable rut extraction technique, which I get to explain to you. I know, last talk of the day, so fun. And I got to use a high resolution digital surface model, which we created from using that UAS. And then I'm also analyzing historic aerial imagery from 20 years ago and 10 years ago and comparing it to that photogrammetry data that we also collected using the UAS. And this was done across 2 wind tidal flat systems across the south of Texas using this bright orange Wingter 1 drone here. And we flew this drone at the Padre Island National Seashore, which is about a 325 acre study site. And then we also flew it at the Boca Chica SpaceX launch station. Yes, I know. And that is about a 50 acre wind tidal flat system. The abbreviation is PAIS for pins, and that was about 1.1 centimeter resolution digital surface model and photogrammetry imagery that we collected. And then at Boca Chica, it was about a 3 centimeter resolution imagery, and you get to see both of our researchers collecting data while we were flying these drones. Moving forward to kind of explain these methodologies to you, I'm really going to be focusing primarily at Boca Chica. So first, to understand the extent of these damages, I will break this down for you, don't worry. But this is one section at Boca Chica. It is a 100 by 100 meter region, and all 5 of these little plots are that same region, just to explain the steps to you. So first, taking that digital surface model, I first smoothed it out to kind of be a representative surface of what this wetland would look like before it had been impacted by damages. And then I created a difference raster by subtracting the 2 from each other, creating positive depth profiles of these damages across the region. So in using this difference raster, I then tiled it up. So once again, this box is representative of like a 100 by 100 meter square. So I either tiled it up by this 100 by 100 meter tile or by these 10 meter tiles. And then I applied 2 different thresholds to these different size tiles, one of which was a 10 class natural breaks of the elevation within these tiles. And then the other was a 75th percentile extraction. So remembering that that depth profile, all positive values, 75 and above, are kind of representative of those ruts. And that was extracted from these tiled surfaces. So what this would look like across Boca Chica area is, this is kind of representative of that 10 meter tile natural breaks classification, where I myself chose which levels of the natural breaks represented those damages. And then this is what it looks like when it automatically chooses that 75th and above elevation, which is representative of those ruts. So to kind of see how well did this do at kind of extracting these ruts across Boca Chica. So it was a 3-step process. So first, I took 3 100 by 100 meter areas as representative regions of Boca Chica, and I drew polygons of damages across these regions. And at Boca Chica, there was quite a few, so it took a while. And then I classified regions with a binary classification of where ruts and no ruts were. And then comparing that manual ground truth, I used a confusion matrix, which suggests what is the similarity between this manual threshold and all the other 2 thresholds that we chose. So to look at the results for Boca Chica, this is the entire Boca Chica wind tidal flat study area with all of the ruts that I extracted across this region. The optimal model was that 10 meter by 10 meter tile natural breaks, which showed a mean sensitivity, or like the true positive of what ruts were there, of about 82% across the region. And these 2 images on the bottom are kind of representative of a close-up view of what that rut extraction looks like. And then across Boca Chica, there's about 20% of this region by the that is impacted in some way in elevation. Okay, and then to also understand, so these damages are there, they keep happening. How long do they stay there? There's some suggestion, Martin 2008, which says that these damages can persist for over 35 years onto the tidal flat, and I wanted to understand what that looked like specifically at Boca Chica. So using 1 meter resolution imagery from 2004, 2014, I wanted to compare that to current imagery. So I also have 1 meter resolution imagery as well as the higher resolution imagery that we collected to see if ruts that I delineate within 2004, 2014 in that higher resolution would be lost over time and would pop up still kind of in that higher resolution, which we'll see in some of the results. So from 2004 to 2023, in both the low and high resolution, we saw only a 7% persistence of damages that were found in 2004 continuing into 2023. However, across 10 years, so from 2014 to current, we saw there was a 31 or 42% persistence of these damages that were created sometime between 2004 to 2014 to current. So that higher resolution picked up ruts that weren't seen in that 1 meter resolution, which makes sense. But so there's such a big jump in this time frame. What might that mean? So I took these numbers are representative of the ruts that I myself delineated across all these time frames, and they are of 3 separate samples that I took at Boca Chica. So there are quite a few damages within these 3 100 by 100 meter regions that I sampled. And purely by imagery alone, I think it's pretty clear to see why this ongoing damage is hard to see. So that 7% is really being occluded by these ongoing and persistent damages across Boca Chica that are continuing to impact the surface. So some initial findings are that currently 20% of Boca Chica in some way is impacted by human damages, and that 7% of damages by this analysis have shown to persist over 20 years, but about 40% of damages persist over a time frame of 10 to 20 years. And this lower resolution and possible ongoing damages might really be occluding the understanding of the persistence of damages in this region. This is super important because of ongoing work, again, to restore these wind tidal flat systems. We are trying to see how much effort needs to be put into elevation restoration and how much these managers need to put into restoring them. So if you want to know more about elevation restoration and cyanobacteria restoration, I really suggest you go to Zara Hassan talk tomorrow. Can't talk anymore. But if you have any questions, let me know. I'd love to talk about it. None? Okay. This one's a 10-meter tile with natural breaks, and then, oh, no, not backwards. This one's 75th percent. The difference is really in what I myself picked. So I think there is a lot more noise in this classification that I picked because both of them were purely based on elevation, which is really what I was trying to detect because they want to restore elevation in this region. So it's not surprising to me that purely using a 75th percentile classification has gotten so much more noise than me myself choosing that threshold. So having this, having the optimal model be one that I manually chose myself is not necessarily surprising. Yeah. Yeah. Yes. So if we're extracting the elevation by different thresholds across the region, so I myself pick like what elevation is kind of like the cutoff between what maybe a normal tidal flat deviation would be and what is like a damage in the region. Mm-hmm. Yeah. Yeah. So I'm working with the Conrad Blucher Institute, and they are working on more of like the imagery analysis portion of this and trying to incorporate more, yeah, linear analysis and orthomosaic analysis. But they wanted me to focus on using purely the digital surface model to try to extract these reds. Yeah. So at Padre Island National Seashore, driving has been closed since like the 70s, is what a park ranger told me today. So if any of you know anything different, please let me know. But that has been closed off completely. At Boca Chica, there really is no limitations to driving on this area, especially when they're trying to pull debris off the region. Yeah, that's a great question. So, a lot of literature on what the recovery after compression looks like is based on arid biocrusts. So, a lot of those papers have shown that after compression, there is a really long time for them to be restored, especially if any of like biomaterial is removed. So, with the other portion of our project, once again, I encourage you to go see Zara's talk, is trying to restore that elevation and trying to re-recruit cyanobacteria in that region. So we don't know specifically for this system, like how long it takes to recover. Yay!
Well, thank you, Isabel, and thank you, everyone, for joining the session. The next item on the agenda is the poster session at 4 o'clock in the Lyceum, which is just through these doors out here and into the main building. So thank you, everyone. Please enjoy the poster session.